My name is Bailey Chapin, and this is my Physics 2211 Lab 3 on the black hole. Let's talk about the purpose of the experiment and the experiment findings. The purpose of part 1 of the experiment is to find the mass of a black hole through a computational model that simulates a gravitational interaction between a star with a known mass and the black hole. In part 2, using another computational model, we will find the initial velocity needed for a spaceship to fly close to the black hole before escaping the black hole system without entering the black hole or running into the planet. Some of the findings were that the mass of the black hole from part 1 was 8.78 times 10 to the 33rd kilograms, and the initial velocity of the spaceship from part 2 was -5 times 10 to the 7th in the x component, 3.8 times 10 to the 6th in the y component, meters per second. The main physics concepts of this experiment is based on Newton's second law, which states that the net force of an object is the change in momentum over time. This law can be further rearranged into the velocity update formula. The position update formula can also be derived from Newton's second law. The next key concept is the parallel and perpendicular components of the net force. The parallel component, or p hat, is the component parallel to the direction of the motion. Positive p hat points in the direction of the motion and is related to the speed of the object. The perpendicular component, or n hat, is perpendicular to the parallel component. Positive n hat points to the center of a turning circle and is related to the change in direction of an object. The other important concept in this lab is Newton's universal law of gravitation. Because this experiment takes place in space, the only force acting on the object is gravity. This slide shows how to calculate the gravitational force. G is the gravitational constant, the two m's are the masses of the objects, and r is the distance between the center of the masses. Here are the free body diagrams for this experiment. In part 1, the system is the star and the surroundings are the black hole in space. In part 2, the system is the spaceship and the surroundings are the planet, the black hole, and space itself. Here are the initial conditions for the computational model part 1. The mass of the star is 2 times 10 to the 30th kilograms. The gravitational constant of 6.7 times 10 to the -11th is also listed here as well. Here are the important equations that are converted into code for this part of the computational model. Here you will see the iteration step for part 1 of this lab, which is used to update the net force, the position of the star, and the mass of the black hole at each iteration step. Here are the results from the computational model part 1. The mass of the black hole was found to be 8.78 times 10 to the 33 kilograms. This was found by averaging the mass of the black hole from all the iteration steps in the computational model. F net was found to be 7.59 times 10 to the 28 newtons, and F net parallel and perpendicular are listed here as well. Let's discuss the results from the computational model part 1. The star follows an elliptical orbit around the black hole due to the gravitational force. The gravitational force is smaller in magnitude when the star is further away from the black hole compared to when the star is close to the black hole. This correlates to the changes in the parallel and perpendicular components of the gravitational force. Some possible sources of error here are rounding errors during the iteration calculations and rounding values of the gravitational constant g, which may explain slight differences in the mass of the black hole at each iteration step. Initial conditions for part 2 of the lab, which includes the mass of the black hole, which was found in part 1 of the experiment. The initial velocity of the spaceship is an unknown in this experiment, and trial and error must be the important equations to code for part 2 of this experiment. Here we can also see the calculations for the distances between the masses and the r hat values. The gravitational and net force equations are converted to code as well. Here is the iteration code for this part of the lab. The velocity and position update formulas are also used in part 2 of the lab. Here are the results from part 2 of the lab. The initial velocity of the spaceship was found to be -5 times 10 to the 7th in the x direction and 3.8 times 10 to the 6th in the y direction, meters per second. The shortest distance between the spaceship and the black hole was 7.721 times 10 to the 8 meters. The initial velocity of the spaceship was found to be -5 times 10 to the 7th in the x component and 3.8 times 10 to the 6th in the y component, meters per second, which means it moves to the left and up the x-axis. A larger magnitude in the negative x direction means more leftward movement and then some up movement as well because of the positive y component. Maximum gravitational force from the black hole was found at the shortest distance from the black hole. The spaceship also seemed to shoot out of the black hole planet system because the gravitational force increased the speed of the spaceship. Some possible sources of error were again the rounding values of the mass of the black hole, gravitational constant, and iterations. This may have impacted the initial velocity value found of the spaceship, which may under or overestimate the velocity values. To answer the what does it mean question, how is the net force and its parallel and perpendicular components different from the rate of change in momentum and its parallel and perpendicular components? As you can see here, these equations show that the net force is equivalent to the rate of change in momentum, which means that the parallel and perpendicular components of the net force are equivalent to the rate of change in momentum, which can also be seen by the equations at the bottom. What if question, what if we went into orbit around the black hole? We know that the new velocity to create an orbit would have to have a higher magnitude in the y component. The new spaceship velocity was found through trial and error, and a velocity of -5 times 10 to the 5th in the x component and 7 times 10 to the 6th in the y component meters per second gave the elliptical orbit shown on the left. The spaceship orbit shown in the purple shows the spaceship orbit around the black hole. Thank you.